Okay, the last part about Wasserstein Generative Adversarial Networks. Generally speaking, so in the year 2020, if we look at what have been the most interesting innovations in computer vision in the last 5 years, I think many people would say it is the generative adversarial networks and related techniques. So techniques that would generate new images. There are a couple of interesting competitors. So the variation autoencoder type of networks and normalizing flows. But all three have interesting properties and have really boosted the way that simulated images look like. So if we look back at the time of Markov random fields, simulated images looked like correlated noise essentially, and well, now simulated images look like those that I showed you earlier today. So if you zoom in, you will find mistakes or oddities, but by and large, it's pretty impressive from how few examples you can now learn to generate points on a manifold that lives in a million-dimensional space. If these images have 1,000,000 pixels, they don't quite, they're a bit smaller, then, well, the valid sleeping rooms, they occupy a manifold in this million-dimensional space, and it is always difficult to estimate densities in a high-dimensional space. So if you think about doing it with a kernel density estimate, you quickly suck sum to the curse of dimensionality. If you want to do it with histograms, imagine how many bins a histogram needs to have in a million-dimensional space and how sparsely the bins will be occupied if you only have a limited number of training examples. So it really is a very hard problem, and amazing progress has been made in that direction. Now, how do Wasserstein GANs approach it? And they were published first. So first author was Martin Ajowski in I think 2017. Basic idea is the following. So here is a sketch of the million-dimensional space of images. In this space, we have a few real example images. They're just points in that space. And, well, we have fake or synthesized or generated images. And ideally, of course, all the synthesized images or all the blue points should be where the red points are. Yeah? But in this example that I drew or invented here, the result is not yet perfect. So just to highlight the differences a bit more clearly. Now, the general idea is that you have an encoding neural network which takes samples from a low-dimensional parametric distribution. So, for example, this distribution is often a uniform distribution or a Gaussian. So here I sampled a few points in one dimension, and then the encoding network turns these, in this case, one-dimensional random numbers into 1,000,000 dimensional, or maps them to points in 1,000,000 dimensional space. In reality, of course, your low-dimensional sample is not one-dimensional. It is, I don't know, maybe 64-dimensional or so, but still the dimensionality is much lower than the space where you are projecting to. So in terms of a neural network, if I were to draw it schematically, this would be a decoding network where you put in your low-dimensional vector that you've randomly sampled, z, and your output is some, invented image, I don't know, x hat or whatever you want to call it, or let's just call it here g of z, where g is now a decoding neural network. So it's like the second half of an autoencoding network, let's say. Good. And well, now we need, on the one hand, something that tells us that in this example here, we're not doing great yet, because we generate blue points that are far away from all red points. That's not good. So we need a way of detecting or of measuring the problem. And then we want to know how to change the parameters in the network in order to make this discrepancy smaller. And of course, discrepancy brings us back to optimal transport and so on as a way to measure discrepancy between two distributions. So let's say that as measure of discrepancy, we want to use the Earth mover's distance. But how do we compute this in a million-dimensional space for many, many points? And there is actually a neat way to measure the discrepancy by again using a neural network if we use a dual formulation of optimal transport. And this dual formulation, I cannot derive it here, but I want to mention it and sort of explain of where this comes from. So the formulation that we need is called the Kantorovich-Rubinstein dual formulation of Earth mover's distance. And when we were talking about the linear programming formulation of discrete optimal transport, we saw this. I did not really derive it because I did not prove the fact that each linear program has a dual linear program. But if you make that leap of faith, and if you accept that by going from primal to dual, the cost vector becomes the constraint vector and vice versa, then that thing here might look sort of plausible, the thing that I've written here in gray. Now, A and B were the source and target distributions. The way it's written here, they don't need to live in the same space or anything. And the way it's written here, the cost matrix can have any arbitrary structure. It need not have anything to do with Euclidean distance or anything else. But if A and B live in a single metric space, if my source and target distribution live in a single metric space with a metric C, then from the fact that I want to maximize this thing, and if I assume now that A and B are non-negative, then it means I want to make alpha and beta as large as possible, but I have also this constraint here. So if I want to make alpha and beta as large as possible, but they must remain smaller than C, and in a metric we always know the distance from a point to itself is 0, and this must so also hold for these diagonal elements. So if alpha and beta should be as large as possible, but alpha and beta must be no more than 0, then it follows that at the optimum alpha I will be minus beta I, and I'm introducing a new name for this. I'm now calling it F. And then we obtain that the Earth mover's distance between A and B is actually given by this thing here. We want to find a function F, also living in that metric space, which is as large as possible where I have lots of stuff in the source, and which is as negative as possible where I have lots of stuff in the target distribution. And we had this constraint here, alpha plus beta should be no more than the cost, and we said that this also needs to hold for the here in the case where C is a metric, and that translates to the constraint that this value of the function at two locations fi and fj, the difference in the values of the function must be no bigger than the distance between I and j. And this is something which is called Lipschitz regularity. And for those who have never heard that word before, here's an example from Wikipedia. There's some curve, and I can now create a cone with a given slope. So here the slope is probably 3 or so. And if I can translate this cone along the function such that the rest of the function always stays in the green area, then I can say the function has Lipschitz regularity of, if the slope is 3, then it would be a Lipschitz 3 function. And I can do the same, of course, with a slope of 1. So it means the earth mover distance between distributions A and B is given by the product of the difference between A and B and some function f, such that this function has a slope that must lie between -1 and +1 at each point in space. And if we now maximize over any such function, then the value of this maximum will give us the earth mover's distance. This is a funny result, perhaps. But I think it's hopefully maybe sort of clear if you come from this duality argument in linear programming. This was hand waving in the sense it was, half discrete, half continuous, and making all kinds of implicit assumptions. You can properly formulate this in the continuous domain, where this earth mover's distance, which is also known as the Wasserstein distance, is given by this expression here, the integral over f of x times a of x minus b of x, such that the function is Lipschitz 1. This is the dual formulation, and then there is a primal formulation also, which says we're looking for the cheapest transport plan. Here it's not called transport plan, but coupling, gamma, and we are looking here for a coupling. A coupling is one which has the correct marginals, as you see here. And we want this Euclidean distance weighted by the coupling to be as small as possible. We're looking for the best coupling. Yeah? And so these statements hold only if, or these equations are, or the definition of the Wasserstein 1 distance relies on this cost function being given just by the Euclidean distance. All right. So in summary, we can compute the earth mover's distance between distributions A and B by finding a function f, which should be as large as possible across A, as small as possible across B, and with a slope with an absolute slope that must not exceed 1. Yeah? The function should not be steeper than +1 or -1 anywhere. Good. And now where do neural networks come in? Well, this function f is something that we can try and represent in terms of a neural network. This is where we now come back to the Wasserstein GANs. So I have now invented in this plot a function f. These are isocontours. So I've shown in bold lines where the zero crossing of this function is. And you see it tries to be as large as possible. These are the non-interrupted isocontours. It tries to be as large as it can where the red points are. It tries to be as negative as it can. These are the dashed lines or dashed isocontours in the area of the blue points. And the best such function will be the exact Earth mover's distance. Now we approximate this function in terms of a neural network. And this Earth mover's distance will be our criterion of how good the blue and the red cloud are overlapping. And so what Wasserstein GAN does is it, on the one hand, tries and improves the neural network that estimates the Earth mover's distance by means of this function f. And then given this function f, it tries to figure out how to change the parameters in the generator such that the overlap of the two classes will become stronger. Because we want the fake examples to have the same distribution as the real examples. All right. And for a sketch, let's look at this. So we have real images. I've indicated an image here by a big vector. We sample low-dimensional random vectors. We put them into a decoder that gives us generated images. So this has the same dimensionality as the real image. And then we plug both into the critic to find out what is the expected Earth mover's distance as an expectation over many real images and many sampled images. And then on the one hand, we try and improve the function f to get a better estimate of the Earth mover's distance. And on the other hand, we then try and improve the generator so as to increase the overlap or to reduce the Earth mover's distance. And so these are two competing criteria, and hence this is an example of adversarial training. So you see the sum over the function evaluated at true examples minus the sum of the function evaluated at the fake examples. So g of z is the generator of my low-dimensional sample. So this is the Earth mover's distance, and we take, or our estimate of the Earth mover's distance, and we take the gradient of it to understand how we need to improve the network, and that's happening here in line 5 and 6, how to improve the network that estimates or that gives us the function f, shown here in the top right, which gives us an estimate of the Earth mover's distance. So we're iteratively improving the estimate of the Earth mover's distance, and that happens in this loop here. And then once we have a decent function f, we then try and improve the parameters of the generator. And here the sign has been flipped. So we try and change the generator such that the points that it generates will lie in the areas where the function f has high values. In other words, it will try and change the generated samples such that they have more overlap with the real samples. Okay, then as a technicality in this original paper, Arjovsky, to enforce this Lipschitz 1 condition, he clipped the weights of the neural network. Later it turned out that it's better to add numerically better behaved if you add a penalty on the gradients of f being larger than 1 anywhere. In summary, Wasserstein GAN tries to find the parameters of an encoder. The encoder maps samples from a very primitive low-dimensional distribution to the space of images. And the aim is to find parameters of the, sorry, it should not be encoder, it should be decoder, excuse me. And the aim of the exercise is to find parameters for this decoder such that the generated images have a big overlap or a small Earth mover's distance to the real images. The Earth mover distance itself is estimated not by solving a linear program or by solving a network flow problem, but using this dual formulation, the Kantorovich-Rubinstein formulation. The Earth mover's distance itself is estimated by a second neural network. And then these two neural networks are trained simultaneously or alternatingly to, on the one hand, get an updated estimate of the EMD, and on the other hand, an update of the neural network that generates the fake images. Good. So this is one example of why it does make sense if you want to do state-of-the-art, if you want to understand or develop state-of-the-art computer vision methods, why it is important to be aware of what problems are efficiently solvable and how to solve them efficiently. Brings us to the end of the lecture. So the curriculum, it's sounded pretty modest perhaps, it's just a few bullet points, but we've covered a lot of ground. You have covered a lot of ground. Yeah? So from the basic, downsampling, upsampling, plain neural network stuff, over very basic algorithms, very basic computer science stuff, until today. Alberto and I were really impressed by how well you did in the exercises. We know they were not easy, and it was a lot of effort, especially in the early ones. I apologize for the late nights that you spent on that, but you did really well, and I would like to thank for the good questions that you've been asking along. I would like to thank Alberto for great exercises that he prepared and very diligent correction of these along with Sebastian. And looking forward to seeing you at least once in person for the exam 2 weeks from now. And I wish you a very successful, end of semester and wonderful summer, far away from all the mess. And we're looking forward to seeing you again in fall. Okay? Thank you very much. Bye-bye.